Hello, my name is Simon Pedley, and I'm going to run through some detection outlines with you today. So I've been working with Leica for nearly 19 years. Spent most of my initial time working throughout Europe, helping customers overcome damage and utility prevention, and also down into the world of utility mapping, so we could understand where utilities are not only now, but for the rest of time. For the past 6 years, I've been focused on the US market, helping drive this change throughout the region. But one of the main questions I always get asked is, what is utilities detection and what's the need? Okay, we hope that when we put utilities into the ground, we had some sort of plan that says where these should be put. But unfortunately, that isn't always the case. We may have an as-built or as it may have been built, but these aren't accurate. We don't have all the information that is required. And we have a massive need to access these utilities to understand and expand this network. We may be repurposing old buildings where we need to have multiple connections going into an old factory, for example, or we may have a break on the line and we may need to repair it, but we don't know the exact location. So these are huge issues that we face. And huge amounts of utility strikes. In the US alone, and we can replicate this around the world, but in the US alone, we estimate that we hit 400,000 utilities every year. If we do some quick maths, that basically means we hit a utility every minute of every day. Okay, that's a huge amount of damage and downtime, and also cost not only to the contractors or anyone working on that project, but also society. If we look at that true total cost, and this information comes from the Common Ground Alliance or the 811, and these do this report every year, but they are estimating that everywhere just in the US, that these utility strikes cost in the region of $30 billion. That's a huge amount of money that's just being wasted, and we can prevent, we can get better at doing these types of things. So how do we go about locating these utilities? Typically, we use two different types of technology. We have what we refer to as induction or electromagnetic locators. These are used to capture signals being re-radiated from underground lines, but these must be metal. So metal water lines, gas lines, power cables, all these things can have a signal being radiated from them. Signals applied from a transmitter, we can identify where they are accurately and understand the location and the position of them. But not everything is metal in the ground. We've got plastics and all other different types of materials, and that's where we would use ground penetrating radar. This works on a reflection or an echo sort of workflow. We send a signal into the ground, it hits something and bounces back. So really, in its simplest form, radar is detecting material density changes. We're just looking for the change in the ground to figure out where these cables and the pipes may be. So, as you'd imagine, there's some standards around utility detection. So here I have the ASCII one just called out, but really, the standards all follow the same process, and these standards change all over the world. We've got them in Japan, Malaysia, UK, Australia. There's a huge amount of them out there. But basically, they follow up the 5 basic steps, should we say. Number one is we've got to figure out what happened over the past 100 or 200 years. We've been burying utilities for an extremely long time. Some cities and some parts of the world, it can be over 200 years. We've had cables and pipes put into the ground. And do we know where these are? Probably not, no. We're probably going to have some gaps. So step one is what we need to do is try and gather as much information about this infrastructure as possible. Let's go through the plans. Let's capture the information from GIS databases and wherever we can get it. We want all the information possible. And then we want to go and try and prove that information right or wrong. And that's where we need to use the detection solutions to allow us to identify where they are. So that's the ground penetrating radar, that's electromagnetic locators. These are the things that are allowing us to do that detection and make that investigation as accurate as possible. Once we've identified where the things are, we've sprayed the sidewalks up, we've done what we've needed to do to prove to ourselves that we've found these lines, we then need to survey it. We need to capture this information and put it in some sort of plan so we have it for the rest of time. And then we need to pass that information on to our client, pass that package over, okay? So really what controls this whole process is the package. What does the client want as the deliverable? But one thing just to touch on as well is what's the value, okay? Why should we go out and try and identify where these utilities are? Okay, what value do we bring to the market? So an investigation here was done by Purdue University, and for every dollar we spend on the front end of mapping utilities, for the whole life cycle of that project, we're going to save over $4. Okay, it's a huge cost saving, or return on the investment, should I say, of what we spent. But basically, if we look at this standard or the way we work, we break it down into 4 quality levels. Okay, D being the worst, A being the best. If I look at ASCII, these can change region to region. Level D is basically gathering that information. You know, where are these lines under the ground? Level C means we've gone outside into the field and tried to make some sense of what's going on. It says there's a water line. Can I see a fire hydrant? Can I see a valve? What information makes me think this is good? Level B is taking it a step further. Let's use some geophysical methods to prove it. What can we find under the ground? Can we prove that we can find that water line with a locator and GPR? We're trying to build up this investigation of where these lines are. Not only are we trying to find what's on the plans, but we're trying to find what's also missing, you know, the unknown utilities, the abandoned services. And then the final piece is level A. This is the most accurate way we can do it. This is when we know what something is and how something deep it is because we've done a trial hole. We can now get eyes onto that utility. We see it, we know how deep it is, and we know what it is. We have confidence over mapping it and giving that quality level to it. Now, what is the technology that we typically use here at Hexagon? So we've got the locators, which I touched on earlier. This is what's going to be used to identify the metallic utility lines. But then we have the ground penetrating radar. Typical ground penetrating radar, the one in the middle, the yellow lawnmower, that is single channel. We walk outside, we push it, we interpret the information. And then we have multi-channel GPR. So what's the difference between these two? So the yellow lawnmower, should we say, or the DS2000, allows us to capture information in one direction. It's a single polarization. So if I look at a meter cube, then I'm going to walk across that area 4 times in 2 different directions to capture that information. If I go and look at a multi-channel area system, as I tow it over that same meter, I'm going to get 32 different profiles. I'm going to get significant better resolution of what's in the ground. It's going to make my job at mapping utilities better and faster. Okay? So which tool is better to use? Should we go for the large scale mapping tow behind vehicle, or do we go for the yellow one? Okay, well that comes down to the size of the area we're trying to map, we're trying to locate. And I've put this onto the terms of a soccer pitch. If I'm pushing the push cart over a soccer pitch, single polarization unit, I can't walk more than 3 miles an hour. I'm going to do a scan every 50 centimeters, 18 inches. It's going to take me 8 hours to get the deliverable for that site. If I then move up to our Stream C product, still a push behind system, but it's 3 feet wide. I can collect a lot of information in one go. I now increase my mapping speed. Now I can map that area, that same soccer field, in 1.5 hours. And when it comes to the tow behind systems, I can do it within 20 minutes. But that then gives me another problem. I can collect a lot of information extremely quickly, but I need to then process that information. I can't do this work directly in the field and lay spray paint in the ground with these large-scale mapping products. So that brings me to the post-processing side. We then have to put it in software to allow us to understand where these lines are. We can interpret them, we can draw the lines, and we can export that DXF or that plan. But because we can tow behind vehicles and run them at 20 miles an hour, we're getting a huge, huge amount of data. So what can we have to make the process faster when it comes to the post-processing side? And that brings us to what we call AI maps. And this is basically, well, it works with Hexagon HXDR, and it leverages state-of-the-art deep learning platform to allow us to understand where these utility lines are significantly faster. So effectively, I'm looking at point cloud data of where the utilities are under the ground. So traditionally, I would see a whole area and I'm picking through it to understand what's going on. With this process now, I can see the cloud data exactly where the utilities are. I can focus on those areas and I can draw these lines in much, much faster. And it gives me a much better resolution, better deliverable, and I can mark and identify where these lines are. But as I've said, these only work with our larger stream products. the tow-behind systems such as the StreamUp and the StreamC. But using this technology, this Hexagon HXDR AI platform, we can do the survey 70% faster than we ever could before. Thank you.